Everyone, welcome to lecture 3. We continue our journey into understanding and solving differential equations. Today I'm going to introduce you to the method of undetermined coefficients. Now up to this point you are all familiar with first order differential equations, and we've also been looking at second order differential equations with constant coefficients, but more importantly they were homogeneous systems. Now before I go on to solving these equations, I want to give you some sort of motivation as to why we need to solve these equations. We know that these equations are very important in applications, especially in engineering, physics, biology, chemistry, as well as engineering. So what I have over here is a simple harmonic oscillator. I have a mass piece attached to a spring of known constant. Right? It's in equilibrium at the moment, but when I apply a downward force and I set this mass in motion, then it wants to go back to its equilibrium position. So there's going to be a restoring force wanting to take it back to equilibrium. You should also notice that the oscillations are almost sinusoidal. It's a back and forth or up and down motion. So if we get to the equations, in order to model this system, we're going to apply Newton's second law for this harmonic oscillator. The restoring force is given by Hooke's law, which is minus kx, where k is the spin constant. And the second equation over here is nothing more than Newton's second law of motion. That's md squared x dt squared plus kx equals to 0. M is the mass of the oscillating piece, and k being the spin constant. So we have a second order ordinary differential equation with constant coefficient, but most important, it's homogeneous. So you'll recall from our last lecture how to solve this. It's pretty straightforward. We let x of t equal to a e to the rt, where a is a constant and r is a constant. The associated characteristic equation for that second order equation turns out to be mr squared plus k equals to 0. And I'm sure every single one of you can solve the quadratic equation for r. The solution that we get is r equal to plus or minus omega I, when omega is equal to root k over n. Omega is also known as the natural frequency of these oscillations. If you had to write out x of t, or the position of that mass piece at any point in time, it's given by a1 cos omega t plus a2 sine omega t, which from observation we would infer would have been sinusoidal in behavior. The constants a1 and a2 are determined by the boundary condition, or what we will call the initial values. Furthermore, we can write the position as a cos omega t plus delta, where many of you would know that a is actually the amplitude of the oscillation, and delta would just be the phase. Now these pure sinusoidal waveforms is in the absence of air resistance or any form of dissipation. So for the first part of the motion, we've ignored air resistance or friction. Now what if we include air resistance or some form of dissipation? For instance, a mass oscillating in the atmosphere, or a mass piece basically oscillating in water. So we've got some heavy damping. This is a bit tricky. So let's try and get that down like that, so lower into it. There we go, we oscillate. So we get some sort of heavy damping going in the middle there. Just like that over there. So what would happen if we include this damping term? How does it change the behavior of our system? Do we still have sinusoidal motion? So let's go back and remodel the problem. So the simplest case that we can take is the damping force Fd being proportional to the velocity of that mass piece. If you write down Newton's second law, you get this equation over here. Again, it's a second order equation, constant coefficients m, c, and k. And again, very important, it's homogeneous in nature. To solve this equation is pretty straightforward. You obtain the characteristic equation, mr squared plus cr plus k equals 0. Solving, we have two distinct roots, r1, r2, but distinct in the sense that it depends on c squared minus 4mk. These give rise to three different physical systems. all depends on what c squared minus 4mk is. Also note from here that c squared minus 4mk is less than c. So R1 and R2 are less than 0. We refer to overdamping is when c squared minus 4mk is greater than 0. You notice very quickly there are no sinusoidal oscillations, and hence the mass piece returns very quickly to equilibrium because of the decay exponential function. You have critical damping, and this is when c squared minus 4mk is equal to 0, and there the roots are repeated, and your displacement function is now given by equation star. Again, if you notice this, there's no sinusoidal motion, so the system returns to equilibrium very quickly, in fact, the shortest possible time. And the last case is when c squared minus 4mk is less than 0. This is what you call an underdamped system. If you look at this very carefully, and if you write down the displacement equation, you have a sinusoidal form enveloped by decaying exponential functions. So the mass piece, the oscillating mass piece, will return to equilibrium after oscillating sinusoidally. And so we have that. So where is this taking us? So far we've included dissipation. What if we included an external influence, an external force on the system? How does it change the physics? So we end up with a system something like this, where you notice now the right-hand side is no longer 0. You have a forcing function f of t, which is an external influence. How do we solve this? And like I mentioned right at the beginning, we're going to introduce the method of undetermined coefficients to actually work out the position x of t of this oscillator. But before we go to the more general situation, let's try and look at something much simpler. So I have a dE over there, d squared x dt squared plus 5 dx dt plus 6x equal to cos t. So our function f of t is now cos t. It's very much like the oscillator in the presence of dissipation. Theory tells us that the general solution in x of t is given by xp of t plus xc of t. xp of t is a particular solution of the equation that you see on the top, and xc is a solution of the homogeneous equation. So, it's natural to first work with the homogeneous equation. That is, set the right-hand side equal to 0. And if you do that, you very quickly see that we have a second order dE with constant coefficient and homogeneous. And like we did before, we will now write out the characteristic equation, which is nothing more than r squared plus 5r plus 6 equals to 0. If you look at this very carefully, you'll see there are two distinct roots, r1, r2, where r1 is minus 2 and r2 is minus 3. And so I can write down xc of t as a1 e to the minus 2t plus a2 e to the minus 3t, like so. You find their decaying solutions, and also the constants a1 and a2 can be determined from the initial conditions set upon by the physical system. Now let's go back to the original equation. So we've got xc, and that's quite nice. That's known. We now need to focus on xp. So the method of undetermined coefficients basically tells us to choose or guess a particular solution of the non-homogeneous equation. Now if you look at the forcing function cos t or f of t, it tells us, let's try something like xp of t equals to a cos t, where a is an undetermined coefficient. If we do that, then we need to differentiate that. Once, we end up with minus a sine t. If you differentiate that twice, this is with respect to t, you're going to end up with minus a plus t. If we now dump that into equation 1, what do we get? We're going to end up with minus a cos t plus 5 into minus a sine t plus 6 cos t equals to cos t. Now, you can very quickly spot the problem. If I now collect terms involving cos t and sine t, one can immediately see that a has to be 0. Now we can't have that. Okay? How about trying something else, like xp equals to a sine t? And very quickly you end up with the same problem, because if you differentiate, you get x prime is equal to a cos t, x double dash is equal to minus a sine t. If you dump that in there, you can see straight away you're running into problems. Plus 5a cos t plus 6a sine t equals to cos t. So if x prime is a cos t, x double prime is minus a sine t. If I do the second derivative, just double check that everything is correct. You got that, plus 6a sine t equals to cos t. Let's collect terms involving sine t and cos t. So there's a sine t over there, there's a sine t over there, so you're going to get something like minus a plus 6a multiplying sine t must be 0. And then you end up with something like terms involving cos t, 5a minus 1 equals to 0. So you can see there's a problem. It still forces a to be 0. So what next? How about choosing xp of t equal to a cos t plus b sine t? Where would this take us? Well, we're going to go x prime or dx dt is minus a sine t plus b cos t. We need to differentiate this one more time. So x double t minus a cos t minus b sine t. Put that in equation 2, what do we end up with? d squared x dt squared, here we have it. It's minus a cos t minus b sine t plus 5 into, use of brackets is very, very important, dx dt minus a sine t plus b cos t plus 6 into a cos t plus b sine t equals to cos t. It looks really messy, but do we have something here? So if we're comparing terms, have a look at this very quickly. If we can comparing terms in cos t, that leaves me with a minus a. There's a 5 here, that leaves me with a 5b. That leaves me with a 6a, and bring that on the other side, minus 1 equal to 0. So there I have one equation involving a and b. The next one is this one over here involving sine. So you have minus b minus 5a, this guy, plus 6b equal to 0. That's equation number 2. It is not difficult to see from equation number 2 that a is equal to b. You substitute that into 1, and for sure as God made little apples, a equals to b equals to 1 over 10. So what have we got so far? We've got xp, we've got xc, and put all of that together, we have our general solution, x of t is equal to xp of t plus xc of t. Let's remind ourselves what we've got. That's 1 over 10 cos t plus sine t plus a1 e to the minus 2t plus a2 e to the minus 3t. And that's our complete solution. If you look at that, try to analyze that very carefully. You know that as t approaches infinity, you notice that the exponentials would die off and we'd have an oscillating solution. So that's the persistent part of the solution, the first sinusoidal part. How can we relate this? We have all electrical engineers sitting here. How can we relate this to electrical engineering? So here's a really neat example of an oscillator type equation method occurring in electrical engineering, which you're probably more familiar with. I want to discuss something called the RLC circuit, which you're familiar with. So this is more a series circuit. Comprises of three components. Main component will be a resistor, a capacitor, and an inductor. And we have a sinusoidal voltage, or what we call an AC voltage. Now, we want to work out the voltage drop over each component, the charge accumulation, as well as the currents and other characteristics for this. So if you apply Kirchhoff's rule, firstly it's very simple to set up circuit using an oscilloscope. We can measure various characteristics of such a circuit involving, for instance, the phase difference between the currents, the voltage lag, voltage gain, the resonance. But just have a look at it from a mathematical point of view. If you look at Kirchhoff's rule, then we notice that the voltage over the source equals the voltage over the inductor plus the voltage over the capacitor plus the voltage over the resistor. Like this. From your knowledge of that voltage, you can write down for the inductor L di dt. That's the voltage drop there, which we call VL. Voltage over the resistor, voltage over the capacitor. This is the source. Now this doesn't look like a second order equation with constant coefficient, but if you look at the link between the current and the charge, we know from high school that current is nothing more than the rate of flow of charge. Hence, if that's true, if R is dq dt, then we have the equation that I've just circled. Now, have a look at the equation very carefully. Compared to what we've just solved, the second order equation, constant coefficients, non-homogeneous because E of t is very much like our forcing function cos t, subject to initial conditions Q of naught is equal to 0, and the initial current in the circuit being I naught. So the method of undetermined coefficients can be applied to actually solve and determine Q as a function of t. I'm going to leave that for homework, but I'm just really chuffed and excited to show you what the final form of Q of t is. And you will recall, you can almost guess the form. If you look at it, you've got three terms. The first two terms are exponential. In fact, they decay exponential functions that come straight from the characteristic equation for the solution xc for the homogeneous equation. The third term that you see there comes from the method of undetermined coefficients, where we assume the form for the particular solution, just like our example, x of t is equal to a cos t plus b sine t, so we end up with that term. You'll also notice that the persistent part of our solution is the third term, that as t approaches infinity, the first two terms will die off. But also very important is the relationship between R, L, and C. And this gives rise to three cases, just like the mechanical oscillator that you've seen earlier. We have damping oscillations, an underdamped system, just like the mechanical oscillator. You find that you have sinusoidal behavior, but it's enveloped by two decreasing exponential functions. This is when R is less than a root of 4L over C. When R is greater than 4L over C, you have an overdamped system. So the oscillations, so there is no oscillations, and the system reaches equilibrium very quickly. And the last one would be critically damped, which is when R is equal to root of 4L over C. Now the RLC circuit has very important applications in electronic engineering, electrical engineering. One of them would be fine-tuning of circuits, for instance, your television set, your radio set. So basically it's an interplay between L, R, and C to obtain optimum results, or a certain Q factor, as they would call it. Also very important is if there's an associated frequency for the forcing function or the voltage. And if that frequency of the voltage now equals the natural frequency response of the circuit, then we obtain what we call resonance. So I'm hoping with this short lecture, I've motivated as to why we need to study such systems. We've looked at second order equations, constant coefficients, but we've just basically moved on from homogeneous to non-homogeneous equations. But more importantly, I've now equipped you with a method of undetermined coefficients to actually solve these equations. I hope you enjoyed that, and in the next lecture, we'll basically look at higher order equations. Thank you very much.